to start recording here. You might not even remember what you wrote, but I've got some feedback for you here. The solutions are up, and I definitely would encourage you to review those solutions. Everybody was kind of in the ballpark of how they did on the first exam, maybe plus or minus, up to maybe 10 or 15 points, something like that. But hopefully everybody felt reasonable about it. It was, again, really good to have the take-home part. I think that really helped people out a lot. And even with that, I ended up dropping everybody's kind of lowest problem to just kind of, because I think that was reasonable to do. So the scores came out pretty good, actually. There was nobody getting 100%, but there was a lot of people that had really strong scores by the time I got said and done with it. But if you ended up feeling kind of crummy about the whole thing, either how you did or just the whole experience of it, once you get your exam back, definitely look it over. And if you feel like you want to follow up with me, we can definitely do that. I've got a lot of office hours. Feel free to come by. Last thing you want to do is just kind of sweep it under the rug, because we do have a test coming up again, and it will be a comprehensive test. So anything that maybe was a weak point or whatever that came out on this exam, you should try to get that sorted out. Some people did really well on generating functions, not so good on the recurrence relations. Some people did really great on the recurrence relations, had more trouble with the graph theory. Everybody was a little bit different. So I can't really give a one size fits all answer. People's strengths and weaknesses vary pretty dramatically, but overall, most people had most of the material, I think, in pretty good hands. So that was the good news. So what we are going to do, guys, we do have 4 classes left, and I'm not going to waste a minute of that time. I want to talk a little bit more about some concepts from graph theory that are very standard in sort of more of the theoretical viewpoint of the subject. So things like colorings of graphs. And eventually, the big thing I want to do during these 2 weeks will probably end up being next week is the Burnside's theorem, which is going to actually be a little bit of an infusion of some group theory. If you remember from your modern algebra courses, a little bit of group theory. I will review it with you. You don't feel like you have to go do a bunch of studying on that right now, but I'll review a little bit of basic group theory that actually comes into this Burnside theorem, which allows us to count arrangements of objects where you sort of want to do them modulo rotations and reflections or whatever, like symmetries of that object. So it's actually very interesting. It's a nice way to kind of wrap up the semester by putting the original counting problems we were doing at the start of the semester together with the graph theory. So you kind of see it all coming together at the end. So I kind of like the way this kind of wraps up in that sense. So let's get into it a little bit. This is in chapter 12 of the book. We are kind of going backwards because the stuff on crossing numbers and planar graphs was a little bit later in the book. But this is graph colorings. And we're going to talk about something called the chromatic number. And I actually did something a little unconventional. I actually put it into one of the questions on your midterm, but I defined the whole thing in the question for you. So even though we haven't talked about it yet, most people did pretty well with this. The idea here, guys, is maybe you have a map or a graph of something. Maybe there's some different regions in this graph. Could be some picture of, I don't know, some states within some country. And you would like to color each of the regions in such a way. So the goal with this is to color the map so that adjacent regions that are next to each other, adjacent regions receive different colors. This is a classic problem in graph theory. Try to make a coloring of the graph so that the different regions all have different colors. So the way that you normally would do this is you would associate a vertex with each region. So I'm going to go back to this picture and draw vertices, which is really just one dot inside of each region. Okay, so I could draw that like so. And then what we need to do is adjacent regions should, of course, have an edge between the associated vertices. So in this case, you would need to have an edge here, and these two regions are adjacent. These two regions are adjacent. These two are adjacent. So are these two. So are these two. So are these two, right? You kind of get the idea here. And you end up with some picture, maybe it looks something kind of like that. Okay? So the idea here, guys, is to put colors on these vertices, but any two adjacent vertices should be different colors. Now, if you want to actually use colors on like your homework and on the exams, that's fine. However, I have to tell you, I am kind of colorblind. I taught this class last year. There was this guy who, first of all, he liked red and green, and which is really tough for me. Where's my red marker somewhere here? And he was doing this. He was just like little dots. I was trying to grade his homework. I couldn't possibly tell what it was. So guys, if you're going to actually color them with colors, make these things really, really thick dots for me so I can see the colors. The other way to do it, of course, is to just label the vertices with the colors. So I could have red is just R. So just use an R for that. And then anything adjacent to red has to be a different color. That would be maybe green. So G for green. Maybe we have white here, right? And then this one could be green again, right? Because it's not adjacent to this other green. This one up here has to be a different color. Maybe this one becomes, I don't know, yellow. Use a Y for that. And then this one could be red again up in this corner. And this one could be white again. So you could color it like that. And just putting the letters next to the vertices would be a good way to keep that straight. Okay. Right, so let's actually put down the formal definition of what a coloring of a graph is. We've kind of explained it in words, but let's just put a definition here that hopefully will make good sense. So a coloring of a graph is the assignment of a color. It is the assignment of a color to each vertex. It is the assignment of a color to each vertex so that no two adjacent vertices are the same color. So that is what a legal coloring of a graph is. It is the assignment of a color to each vertex, basically what I just did here. I put a color on each vertex so that no two adjacent vertices have the same color. And our goal with this, so I said here the goal is to color the map such that you have a legal coloring, but we can actually make a stronger goal, which is to do it with as few colors as possible, right? So the goal, maybe I'll call it, it's the refined goal here. The goal is to color the graph with as few colors as possible. And however many colors that is what I introduced to you kind of cruelly as a question on your midterm, which is the chromatic number of the graph. Okay, so let's actually put it into our notes now. The chromatic number of the graph, right? I want people to know about this. This is a pretty standard topic in graph theory. The chromatic number of a graph, G, is the least number of colors needed to color the graph. And this is denoted, as you saw on the exam, it's denoted kind of with this script X. It's called chi. It's a Greek letter chi, C-H-I. So chi of G. And that is standard notation. It's not just from this book. It's pretty well established. So we should try to use that for the chromatic number of a graph. Okay. The fewest number of colors that we can get away with. So for a couple of quick examples, first of all, so the first example, I guess, by the way, slow me down if I'm going too fast or if there's any questions here. I'm just basically giving you kind of the background, but if I'm writing too much too quick, stop me, you know. So the first point is, well, what if there's no edges? So if G has no edges, so this would be, i.e., it's called a null graph. A null graph is just one that does not have any edges. Then, how many colors do you need?
One.
Yeah, you just need one color. You can just color every vertex the same color. And so the chi of G, the chromatic number, is just one. And in fact, that's if and only if. I probably should point that out. So this is chi of G equals 1. This is if and only if G is null. No edges, right? That's pretty straightforward. Okay, so if there's any edge at all in the graph, you would need at least two colors. Because the two vertices that are connected by an edge would have to be different colors. That would be two colors, right? So that's the first point. For a second example, that was kind of the opposite extreme, would be the case where you have every possible edge in this graph. Let me come over here. Sorry, I'm using my battery's almost dead on my phone here. So the second case is that chi of G, so if G is equal to the complete graph on n vertices. So this is the graph where we have every possible edge between any two vertices. Then how many colors would you need in order to color this graph? N, actually. So if it's Kn, then you have every possible edge. So any two vertices have to be a different color. I got n vertices here, so that makes sense. This is actually the worst case scenario. Like in the case of the complete graph, you need n different colors. No two vertices could ever be colored the same because they're always connected by an edge. Right? And so for any graph of order n, you would never need more than n colors, but in the case of the complete graph, you actually do need n colors in that case. So that's kind of the opposite scenario. The third one, the third example I would give you is actually the one that I asked you about on the exam, and most people did a really good job on this, at least some people did it in class, some people took it home, but either way, I was really happy with this, which is that G is a bipartite graph. Remember, that's where you have two camps of vertices. And the thing is that in a bipartite graph, the vertices within a given camp can all be the same color. And the vertices in the other camp can all be the same color. So in this case, the chromatic number is never more than 2. Of course, it could be 1 because a null graph is also a bipartite graph. And a null graph would have a chromatic number of 1. So this one, I can just say C midterm 2. We certainly talked about that one in the exam a little bit, and you can certainly read my solution to that. We sort of did the proof there. But that's a good example to have in our list as well. Another one that's kind of interesting is if G is equal to, I'm going to call this C sub n, where C sub n is a single n cycle. So if I just have a cycle, one single big, all the vertices are just arranged in a big circle, basically. And there are n vertices, so this could be a pentagon, a hexagon, a septagon, it could be just a square, right? Something like that. Then how many colors am I going to need to color that kind of a graph? Does anybody want to take a guess at it? So as I'm going around the vertices of a circle, I could go from red to green to red to green to red to green, right? So that would be 2. Does that always work?
Depends if it's odd or even.
Right, it depends if the graph is, because if there's an odd number of vertices, then if you start with red, green, the next one would be red again, which would connect to the original red vertex. In that case, you would need 3 colors. You would need 1 extra color. So this one is 2 if n is even, and it's 3 if n is odd. So that's another nice example. So obviously, well, you could use that to prove that the cycle graph on an even number of vertices is bipartite, because in that case, you're only using 2 colors. Kind of makes sense, okay? The next example is not really an example. It is a famous result in graph theory. Number 5, this is called the 4-color theorem. And this is kind of interesting. The 4-color theorem is a famous result that says that if G is planar, so if I can draw my graph without having any crossing edges, then it turns out that you should be able to color it always with no more than 4 colors. That's the 4-color theorem. You can always do this. This was not an easy result. This is actually very difficult. We certainly are not going to prove it. In fact, the proof that exists even today is basically a messy computer. It's a computer program that basically does a million scenarios. It's an algorithm for how to color it with at most 4 colors. I remember when I was in grad school, I was walking down a hallway one day and I was overhearing some professor talking to his PhD student. I'm not making this up. He said, you know, he was doing some kind of graph theory research. Said, what would I need to get my PhD or whatever? And the professor, these are his exact words. A 1-paragraph proof of the 4-color theorem would suffice. Like they're still looking for a better proof of this result. This is not a nice theorem to try to prove, and it would be nice if there was a simple result. If anybody wants to prove that in a paragraph proof, I will exempt you from everything else in the class. Well, not have to do anything else. You'll be good to go, because that is definitely a big theorem. So anyway, so that's just a fact. That's not something we're going to get any deeper into. I haven't really studied the proof myself. Every time I think about doing it, I just get so uninspired because I have not heard anybody talk about this as being like an exciting proof to study or to learn about. It's just kind of a technical thing. So we'll just leave it at that. But it is kind of nice to know it's a famous problem in group theory. Kind of like the whole idea of characterizing Hamilton cycles is another really tough problem that doesn't have a lot of results and is very much still up in the open. Yeah, this was proved in 1976, I believe, for the first time. So it's been around for, that's just about 50 years almost. Okay, another definition related to this whole concept of coloring a graph. Let me continue over here. So let's say we have managed to color G. So if G is colored using, let's say, K colors, let's say we've colored it using K colors, then what this basically does, guys, is it partitions the vertices into groups according to color, right? So then we can partition the vertex set, which remember we usually call that capital V, into K disjoint subsets. We could call those V1, V2, and ... up to VK with the union, where I goes from 1 to k of v sub I, the union of all of those subsets would be the entire vertex set V, but they're disjoint, so they have no overlap, right? Where V sub I consists of vertices colored with, I'll call it color I, whatever that color is. So it could be red, could be green, whatever. So we can do this, right? We can just take our graph and break the vertices up according to the different colors that are used. This is called the color partition of the graph. So this is a color partition of G. Nothing really that deep about it. You're just basically breaking up the vertices into these groups according to which colors they have. The union of all of them, the union of all of those camps is the entire vertex set V. So it does ring a bell of like what bipartite graphs were about a little bit, but it's more general than that because the number of colors could be anything here. K could be much larger than 2 potentially. Okay, but yeah, you have no vertices within any one of these V sub I subgraphs, right? So V sub 1, they're all colored red. Well, then they can't be adjacent to each other if they're all colored the same color. Yeah, was it?
Just a question. I was thinking about the tree. The tree would be 2, right?
The chromatic number of a tree is a really good question. There's no cycles in that graph, so it's kind of the opposite of this scenario. So you could start somewhere in your tree and give it whatever color you wanted, and then just go out in all different directions, alternating colors. Absolutely true. That's absolutely true. Yeah, that would be. You want to add that down? We probably should. This is 6 due to Jose. Give credit where credit is due. If G is a tree, then the chromatic number of that tree is 2. Yeah, that's a good point. So we'll add that as number 6 on the list. Don't know if that's going to reach all the way over there, but number 6 just says that if G is a tree, then its chromatic number is 2. Okay. Well, with that in mind, of course, it would be great to figure out the chromatic number of every graph. That would be a goal. What's the best you can do? And so we would love to have some more theorems, kind of the flavor of the 4-color theorem that could help us. And as you probably would expect, there are lots of theorems that give lower bounds and lots of theorems that give upper bounds on this chromatic number. Not so many that are like number 3, where we pretty much get a direct if and only if characterization of something. So usually it's a theorem that just gives a bound. Oh, the chromatic number has to be at least 3, or oh, it has to be at most 5, or something like that, right? So it's often of that nature. So I'd like to write a couple of those down for you, just so we can kind of see the spirit of how these results often look. So this first one is actually, it's in the book as a corollary 12.1.3 already. And let's just write this down. So let's let G have order n. Have a graph of order n here, right? And this is kind of an interesting thing. We'll do an example in a second to understand this Q that I'm going to bring into the statement here. So Q, we're going to let Q be the largest size. So it's a number. Q is a number. It's the largest size of a subset of the vertices V, which contains no edges. So in other words, now it's not necessarily easy to figure out what Q is. You look at your graph and you ask yourself, what's the most number of vertices I could gather together such that the subgraph that they generate is null? There's no edges no edges among any of those vertices. So you have to kind of tinker with your graph to figure out what's the optimal way to do this. But if you can figure out what Q is, then this corollary will give you a nice lower bound on the chromatic number. Namely, the chromatic number of this graph has to therefore be at least, and it's interesting, it is the ceiling of n divided by Q. It is the ceiling of n divided by Q. Does this at least make some intuitive sense? First of all, n over Q might not be a whole number. The chromatic number is definitely a whole number. So we're going to jack this thing up. Everybody's familiar with the ceiling notation. I hope this is just round up, basically. So this has to be an integer. So if you come out with, 3.7, well, then you might as well just jack that up to 4. The chromatic number would be at least 4. The other thing is that the larger Q becomes, if you can find lots and lots of vertices that have no edges amongst themselves, then that means you can keep reusing that same color on all of those vertices. Overall, that's going to bring down the chromatic number of the graph. You can see that as Q gets bigger, the potential to have a smaller chromatic number also becomes bigger, right? You can have a smaller value there. So at least the theorem makes a little bit of reasonable sense. I'm actually going to try and prove it for you though. As a formal proof, I think we can do it pretty easily. The hard part about this corollary is actually just figuring out what Q is. If I give you a specific graph, you have to kind of convince yourself you have found the largest size that you can. And that's maybe not always obvious if the graph is really messy. But the result itself is actually pretty easy to prove. And so I'd like to write it down here. So far, everybody with me, okay? Okay, great. So let's do this. Just for notation, I'm going to go ahead and call the chromatic number of my graph K. So we'll just go ahead and assume that it's K, and that just means I'd like to show that K is at least the ceiling of n over Q. Okay, so we'll just set that up. And what I'm going to do then is once I have my K colors, I'm going to create the color partition that goes with that selection of colors. So I'm going to let V1, V2, up to VK be a color partition of G. Okay, so we've got the definition over here, where basically we're just partitioning the vertices into these different colors. Okay, and we've got K of those subsets because we've used K colors here. That's kind of the idea. Okay, then, well, we know that within each one of these VIs, there are no edges. Right, so each of these V sub i's consists of vertices that are all colored with the same color. If they're all colored with the same color, then they can't have any edges between them. So your Q here, which is looking at sizes of subsets that have no edges, well, that Q would have to be at least as big, because it is the largest. It would have to be at least as big as the size of any of these, right? So then for all I, K is greater than or equal to the size of V sub I. That's the main point, really. Excuse me. So then, if we take our graph, which has a total of n vertices, so that is the number of vertices in the whole graph. That is comprised of each of these individual vertex sets that are corresponding to our partition. So the size of V is just the sums of the sizes of the subsets. These are non-overlapping subsets whose union is the entire vertex set. But each one of those is less than or equal to, oh, you know what? I made a typo, didn't I? I meant to write, this should not be a K. This was supposed to be a Q. Did everybody catch that?
Yeah.
If not, no worries. Let's fix it right now. That's a Q, not a K. That's supposed to be a Q. That was I made a whole big story of that, right? Q is the largest size of any subset that has no edges. None of these have any edges, so the Q is larger than or equal to all of those. Yeah, exactly. That's what I meant to write. So now I can replace each of these vertex set sizes with Q. And I got K of those. I've got K of those, so that's K factors of Q added the just Q plus Q plus Q. K times, that's just K times Q. So actually, if we solve for K now, K will be greater than or equal to N over Q. And since K is obviously an integer, we can therefore say that K is greater than or equal to the ceiling of N over Q. So that hopefully makes a little bit of sense. Okay, that's the end of the proof. That's the end of the proof. The K is representing the chromatic number here. So that's a good one. Questions on that? Seem okay? Maybe I'll just do a quick example. I mean, it's a nice result. It's not very hard to prove it, but I would say that, you know, the amount of work to figure out what Q is might not be much less than just trying to color the graph with, you know, actually just figure out what the chromatic number is directly, right? So I'm not sure this really saves us a massive amount of work, but let's just, I'll see what you think. Let's just do an example. Let's see if we like what this corollary allows us to do. So just get an example here. I'm going to draw a fairly big graph with about 10 vertices on it. I'll start with one that's kind of up at the top, and then I'm going to make 3 kind of below it directly on a line like that. In a minute, I'll come back and, well, actually, let's go ahead and start putting some edges on. I'm going to make all of the edges connected to the top vertex there like that. And then I'm going to make another vertex kind of on the next row down. Just a single vertex here. And this one is going to connect back to the top as well, like so. And I'm going to make a second vertex on the same level as that one. And we're going to connect across on these two, like that. But this one on the left also connects to the one on the second row on the far left and on the far right. So like that. And then I also want to connect from the very far left to the one that's in the middle on that second row. I forgot to draw that one earlier. And then I'm going to make 3 more vertices kind of down below here. Okay. Hopefully you guys are keeping up with this. I'm trying to narrate my graph a little bit. And the one that was in the middle of this pentagon shape is going to connect to all 3 of those. We're going to connect all 3 of those like so. And then there is one more vertex at the bottom that connects way back up to the top again. Wow. Way back up to the top, and also connects to the 2 on the bottom that are on the right side of that group of 3 that's right above it. Something like that. And I have a few more edges I'm still missing. This one that's on the bottom left should also connect to the one directly above it, and also to the one directly to its right. So I should have that vertex in there as well. And the one that's on that second row in the middle should connect to the one on the right as well. It should look something like that. I think I have everything now. Just double check my graph. Yeah, I think that's looking pretty good at this point. Yeah. Okay, so I just want to figure out the chromatic number of this graph, or at least this figure out what this bound is. So the way that we could do that is, so using this graph, the question is, you know, what is Q? It's really the question. What is the largest subset of vertices that you can take where there would be no edges? Notice that N is 10 here, by the way. We have 10 vertices, but the question is, what is Q? What is the most vertices that you could choose that there would be no edges among them? So you want to kind of the strategy is going to be to look for vertices of low degree because they don't connect up to as many things, right? Maybe I'll get a different color marker here. And there would be many ways to analyze this, but like here's a low degree vertex here, right? It has only degree 2. And it's not connected, for example, to this vertex. So you could circle that. And then you would try to look for another vertex that's not connected to either of those. And you could pick, well, this one over here, for example, is not connected to either of those. And then is that the best we can do? Or is there another vertex that's not connected to any of those 3? One very way down on the bottom. So far I've got Q is 4, but could it be more? Like you have to kind of guess a little bit about that. Would there be is there any other vertex that we didn't circle that's not connected to something that we have circled? So this one won't work, this one won't work, this one won't work, this one won't work, neither will that, neither will that. I can't circle another vertex. Does that mean that Q is 4?
Maybe.
Well, maybe, right? Because it could be that we just didn't do this very well. Maybe we need to scrap the whole thing and start over and maybe a different set of vertices to begin with. We could have actually gone farther and gotten 5, right? So that's the trouble with this corollary is figuring out what is the best choice of Q. We're not going to spend any time like devising strategies for that. This is kind of just something that you have to play with a little bit, but it is going to turn out to be the case that Q is 4. And so thus by the corollary 12.1.3, the chromatic number of this graph is at least the ceiling of 10 over 4. 10 over 4 is 2.5, so that would be at least 3. So at least now you know that you should at least try to use, that you would need to use at least 3 colors. You cannot get away with only 2 colors. Of course, if we did use only 2 colors, that would mean the graph was bipartite. So somehow this is not bipartite. Well, I can actually, it's interesting. I can see that it's not bipartite because I see the odd cycles. You guys remember that? If there's odd cycles in the graph, it's not bipartite. But it's interesting that the cycles don't just use the blue color. They don't just use the vertices that we've circled. They actually use other vertices as well. That's kind of interesting how the result works. So the challenge would be to see, can you actually do this with only 3 colors? And of course, you could look and ask yourself, well, there could be a K4 subgraph here. That would require at least 4 colors. But you can just start. You can start and say, I'm just going to start trying to do it. So here's yellow. I have to choose different colors here, maybe green and white. Yeah. And then I could go back to yellow here. Try to reuse the colors as you go. By the way, what I'm doing right now is going to be written down in an algorithm in just a minute. So I'm basically giving you an algorithm for optimally coloring the graph. So I make that one yellow. I come over here and say, can I reuse something that I have already used? If so, I should do it. So this vertex I could make green because that one's not connected to that one, for example, right? And then this one actually could be, well, this could be white again, if I want, right? And then this one here cannot be white or yellow, but I could use green again, right? So I'm doing pretty good so far at only using 3 colors, right? What else would I need to do? This one could be also green. And this one could be yellow again, right? And then this one could be white again. I think I did it. Yeah. So actually what I just did, this coloring shows that the chromatic number of this graph is at most 3. So you remember when you were doing the crossing number of a graph? There were like 2 parts to it. One part was to theoretically show me that there would be at least a certain number of crossings. And then the second part was draw the graph that has just that number of crossings so that it would be at most that number. So you see, this is a 2-part thing. The chromatic number is at least 3 from the theory, but it's at most 3 because I just colored it with only 3 colors. And so thus, the chromatic number of this graph is exactly 3. So you do it in kind of 2 parts, the same way that you do crossing numbers in 2 parts. So you show how to color the graph using the number of colors that you want, and then you show that you could not have done better than that. And that's essentially the 2-part process. Okay. So far, so good? Good stuff. I love this stuff. Okay. That's a result that gives us a lower bound on the chromatic number of our graph. I'd like to share a result that is going the other way, which in other words is going to give us an upper bound on the chromatic number of the graph. So let's do another result. This is theorem 13.1.5. And this one just says, let G be a graph such that the maximum degree of a vertex is, and I don't know why the book chose to do this, but I'm going to be consistent with the book. They used a capital delta as the symbol for this. So suppose that the maximum degree of a vertex is delta, then the chromatic number of this graph is at most delta plus 1. This one's a little easier to use than the corollary, because in the corollary we had to sort of fumble around to figure out what Q is. The delta over here is a lot easier to figure out. The maximum degree of a vertex, well, we can all go through this graph and figure out what's the biggest degree of a vertex. I see a vertex of degree 5, I believe, in the center there. So this theorem would tell us that the chromatic number of this graph is at most 6. Right, so you take the delta and add 1 to it, which is consistent with what we came up with, but it's certainly, again, it's only an inequality. It's not going to give us the exact value. Okay, a question, Linda. Oh, I'm sorry, 12 point, yes, thank you. I got my numbering wrong. So sorry, 12.1.5, thank you. Yeah, so let's do the proof of this result as well. And it's essentially following the procedure I used to color this graph a moment ago. So you'll see that, I think, when we write down the proof of this. Okay. So proof, and I'm going to actually call this an algorithm. It's really a procedure for doing the coloring. Like, it actually gives us a method for how to color our graph in this optimal manner. Okay, so let's just label our vertices first of all. So just for the sake of the proof notation, so label the vertices. I just chose to label them x1, x2, x3, and ... up to xn. So it's a graph of order n, let's say. And so we can label those vertices, and you can imagine I'm going to start with x1 and color it, and then I'm going to go to x2 and color that. And I'm just going to go down the line, and I'm going to try to never use more than that many colors, delta plus 1. Okay, so let's just color x1 with color number 1, whatever color that is. I don't want to get specific here in the proof which colors I'm using, but let's just take the first vertex and use our first color to do that. And then we go to the next vertex, and as much as possible, we keep reusing colors that we've already used. So in the case of x2, so if we consider x2, I think this proof will make sense, guys. Try to understand it as we're going along. If I'm writing too fast, just slow me down, because I do want you to be able to think about this, not just frantically writing it all down. There's a fair bit of writing here, so I get carried away sometimes on this frictionless board. If we still use chalkboards, I would go slower, but they got rid of those years ago. Yeah, so here's the idea, guys. If x1 is adjacent to x2, then use color number 2 for x2. So if they are adjacent, then you have to use a different color, right? Because if there's an edge between them, they should be different colors. That's the rules of coloring that we have. Otherwise, if they are not adjacent, let's reuse color number 1 again. Use color number 1 for x2. Okay. And let's just kind of imagine we continue this process and we kind of get to some point later on where we're going to consider, let's say, the ith vertex, x sub I. Now, there are at most delta vertices that are adjacent to xi. That's because the degree of a vertex is never more than delta. So there are at most delta different colors that are not allowed, basically, for this vertex. Let's say this vertex, worst case scenario, it has degree delta, and all these other vertices are all different colors, right? Well, then you've got the delta plus first color that's still available to you that you can use. My point is you're never going to have to go beyond delta plus 1 color. So let's write that down. For x of I, there are at most delta vertices adjacent to x sub I by assumption. Yeah, so it's kind of a paragraph. You have to kind of write this one out in words a little bit. By assumption, there are at most delta vertices adjacent. And so some color in the list from number 1, number 2, number 3, ... up to delta plus 1 is not used. Is not used by an adjacent vertex. And thus can be used to color x sub I. Yeah. And that actually applies all the way through the whole graph. As we go from x1 to x2 to x3 to x4, we never get to a point where we've run out of colors from this list. Yeah. So we can make that work. So we can color all vertices with delta plus 1 colors. That's for sure. That's for sure. Now it doesn't, again, it doesn't give us the exact chromatic number. It's not necessarily as efficient. If I had been willing to use 6 different colors here, I wouldn't have had to struggle very hard. But to try to get proof that the chromatic number was exactly 3, I had to be real careful and reuse the colors as much as possible. So that's kind of the idea here. Okay. Questions, guys, so far? We've got a lower bound on the chromatic number. We've got an upper bound on the chromatic number. They're really unrelated. The two results really don't have a lot in common, but it's nice to be able to kind of work at it from both ends. Charging up my phone as I go. Hopefully. Everybody okay?
Can you explain the plus 1 part?
Sure. So in the worst case scenario, when I get to this ith vertex, if it really was of degree delta, it might be that all delta of those vertices could be red because they might not be connected to each other. But again, in the worst case scenario, maybe they're all connected to each other. right? So you would have already used delta different colors for all of those vertices, so you would need one more color. Because you wouldn't be allowed to use any of those delta colors that are being used by the adjacent vertices. So we have to do this +1 business just to take care of that possible scenario. I mean, you can think about it, if you actually had the complete graph and you run this algorithm on the complete graph, you will keep finding that, oh, everything is degree, maximum degree that you could expect. So you always have to keep using a new color every time, and you end up with a pretty high chromatic number that way. Yeah. Okay. Great. Hey, we're doing fantastic here. I think that's all I'm gonna say about the chromatic number for the moment. But of course, it's going to continue to get talked about as we go on here. So that is one interesting question about about colorings of graphs. How few colors can you get away with coloring a graph so that adjacent vertices are different colors? I would like to leave it at that for now and bring up a different question, which is, all right, we have our graph, we have not colored it yet. I would like to know how many different colorings could I do based on a certain number of colors that I might have. It's a different question completely. Completely different question. Can I write that down? I don't want to get confused with this. Here we're just looking for one coloring that uses as few colors as possible. And we've said, we've only talked about it for about 40 minutes, but we've got some nice results on it. And I think, you can play with a graph and get some practice with that. But this next question is, a must do in a combinatorics class, because we've done so many counting problems already. And this is really going to bring us back full circle to counting arrangements of things again. So I think you're going to like this. So given a graph G and K colors, and maybe we can even put them into a set, say 1 through K. So if I have a graph and I have K colors like that, the question is, how many K colorings, I'll come back to this in a second, what this means. How many K colorings of G are there? So I probably should have defined this first, so let me put the definition kind of right below the question here. A K coloring of G, if I want to do a K coloring of this graph, it is a valid coloring of G using some or all. Notice I said some or all. You don't have to use all the colors of the K colors. So a K coloring of G is a valid coloring that uses some or all of these K colors. All right. So K might be 5. It doesn't mean I have to use all 5 colors. I might only use 4, 3, 2, or 1 color. And then let me make a little notation here. So given G and K as above, so just taking those same notations again, taking the graph and taking the K as above, the number of K colorings is written P sub G of K. P sub G of K. All right. So P sub G of K. As I increase K, if I give myself more colors to work with, chances are P sub G of K is also going to increase. This should be an increasing function. So we have PG of 1, PG of 2, PG of 3, PG of 4, right? As we add more and more colors, the number of ways we could color the graph using those colors should go up, if anything, right? Not down. And in fact, as a quick, maybe the first remark that we would think about here is that if K was less than the chromatic number of the graph, so again, I said we're not done talking about the chromatic number of the graph yet. If K was less than the chromatic number of the graph, then how many ways would there be to color that graph using those K colors? That would be 0. Because if you have less colors than what was the minimum number, remember the chromatic number is the least number of colors that you could use to color the graph. If I give you even less colors than that, you cannot color it. So like the complete graph K5, if I only give you 4 colors, you won't be able to color K5 using only 4 colors. You would have to have at least 5 colors. So I think that at least makes sense. We should, as long as we're at it, we should think about the null graph, because that was another sort of easy case. So if G has no edges, then how many ways would there be to color it? So if there's no edges, guys, we're talking about a graph that is literally just a bunch of dots. Right? And I'm letting you use K different colors here, right? And so how many choices do you have to pick a color for this first vertex?
K.
K choices, right? What about the next vertex?
K.
Still K, right? Still K. All of them are just Ks, right? The answer is K to the n, right? It's just going to be the multiplication principle, actually. Each of these has K choices. There are n vertices in total. I'm assuming the graph has order n. I guess I didn't officially state that, but that's kind of assumed. So I'll just say order n here. So if G has order n, then P sub G of K would just be K to the n. Exactly. Okay. Speaking of the complete graph, so that's the other. So this is the null graph. Let's talk about the complete graph. So far, so good. Kind of an interesting problem. How many K colorings are there? Okay, let's do another example. Let's take the complete graph. So if G is equal to Kn, that would be our complete graph. Let's think about what P sub Kn of K would be. So if we need an example kind of to think about, we could come over here and draw, I don't know, maybe I'll draw K5. We have our little pentagon on the outside, and then we draw the star fully connected inside. All edges are there. And yeah, is that good?
Just a quick sanity check. Those are different Ks. The case in
Yeah, this K is a capital K for the complete graph.
Yeah.
And this is the little K is the number of colors.
Okay.
Yeah, I can just use a G here because I've already said that's what G means. Might look a little bit better. Yeah, so let's just think about how many ways there would be to color this. I'm going to start with any vertex I want. It's all symmetrical. I don't really care where I begin. How many choices do I have to pick a color for the first vertex I want to use? Okay, choices, right? And then I can go to any other vertex I want for the next vertex. And how many choices will I have for the second vertex that I color?
K minus 1.
Yeah, K minus, maybe it's just that one, right? K minus 1. Then I pick any other vertex to go with from there. How many choices for colors will I have for the third vertex?
K minus 2.
K minus 2. Do you notice I have to pick a different color every time? So this just goes down from K in kind of a permutation style. of a formula. And in fact, what this should be, I believe, is K times K minus 1 times K minus 2 and dot, 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 all the way until we get to K minus, I think it would be N plus 1 would be the last term. There should be a total of N terms there. I think that should cover it. It should look something like that. So in other words, actually, if you want to, I said we're gonna kind of harken back to the beginning of the semester. This is just a permutation formula. This is what we used in the old days, the P notation. The good old days of September or something, right? This is just P of K, comma, N. Which in other words is just K factorial divided by K minus N factorial. Yeah. And notice again, guys, if N is bigger than K, if N is bigger than K, this, you will pass through 0 here. One of these factors will be 0 and the answer will be 0, which is consistent with what happens here. If I give you less colors than the chromatic number of the graph, it's going to give you 0 for an answer. So that could happen there as well. Yeah. Yeah, because you can see, obviously, the other thing is if K is less than N, then this doesn't even make sense. You have a negative factorial here. So you should probably, you should make the comment here, note that K should be greater than or equal to N. Otherwise, it doesn't even make sense to talk about it. If K is less than N, it doesn't even make sense. There would be no ways to do it. Okay, let's do one that's a little more of a brute force example where we have to be careful about choices and cases and stuff like that. I think that might be helpful. Let me do it over here, I think. All right. So I'm going to draw another graph. This one's not too hard to draw, but I want to do the following example. Find P sub G of K, where G is below. So I'm going to draw a graph, and this will not be, any particular standard graph. So I'm going to draw kind of a triangle on its side here on the left. And then I'm going to add 2 more vertices off on the right that make kind of a trapezoid out of the top 4 vertices. That's the whole graph. That's the whole graph. And I'm even going to label, in this case, I'm going to actually label the vertices A, B, C. I'm sorry, I'm going to do A, B, C like this, and then D, and then E. And this is the example I want to try. So you probably notice the A, B, and C are forming a K3 here. I'm going to have to choose different colors for all of those vertices. So I could kind of start from that. So, so for the solution here, right? So the question is just how many choices do we have all the way around to color this graph? I have K colors available. So there are K choices for vertex A. By the way, there's nobody telling us where we have to start, but I'm just choosing to start with A over here. Then there would be K minus 1 choices for vertex B. I'm just going to use ditto notes there to speed this along just a little bit. And then there are K minus 2 choices for vertex C. So far, it's just K3 on kind of the left side here. Just kind of a copy of K3. And now we come to vertex D. Okay, so this is where it gets tricky, guys. This is where we have to kind of turn on our thinking cap a little bit. You see why it's a little tricky now? I mean, you might say it's easy. D can just be anything except what B was. Which is true. That would be K minus 1 choices, but there's a problem. the problem is that depending on what you choose here, it will affect the choices you have for E. Because you could choose D and A to have been the same color. In which case you would have more different choices left over for E than if A and D were different colors to begin with. That sounds like cases that we need to think about, doesn't it? Right? Vertex D may or may not be the same color as vertex A, and depending on whether it is, that's going to affect vertex E. You see that? Okay, so that's the tricky thing. So I'm going to do case 1. Vertex D is the same color as vertex A. So A and D are both, I don't know, green, whatever. Now, the thing is, if we are in this case, then we had no choices about D. Vertex D had to be the same color as vertex A, which we had already colored. You see this? So there's no choice here. We are forced, in this case, if we're in this case, vertex D has no choices. It must be the same color as vertex A. So we can move on to vertex E. And in this case, if A and D are the same color, how many choices will I have for that last vertex?
K minus 1.
K minus 1, exactly, right. So then we have K minus 1 choices for vertex E. Okay, and so that really at that point, the whole graph has been colored and we can ask ourselves, well, how many choices have we made? So by the multiplication principle, we have, so what is it? K for the vertex A, K minus 1 for vertex B, K minus 2 for vertex C, and then K minus 1 again. I'm going to put that as a square. K minus 1 squared. Choices. Well, let's just say not choices. Let's just say ways to color the graph using the K colors. In this case, that's what we would have, yeah. But that's only one case. We also have case 2. And in case 2, we would assume that vertex D is not the same color as vertex A, right? So here, vertex D is not the same color as vertex A. In this case, that's what we would say. Well, that means now we actually do have choices, yeah, about what color we use here, yeah? Is everybody with me? So if it's not the same color as vertex A, how many choices would you have for that vertex?
K minus 1.
Right, it just has to be different than vertex A, right? So there are K minus 1 choices. So there are K minus 1 choices for vertex D. And we have explicitly said that it's not going to be the same color as vertex A, which means how many choices are left for yes, question.
K minus 2 choices for D, is it also can't be the same color as B?
Oh, right. Vertex D should not be the same as B. Actually, yeah, so it's not the same as B and it's not the same as A. Yeah, that should have been a K minus 2. Thank you. See, I forgot about that. This is a K minus 2. Sometimes I make little mistakes on purpose just to make sure everybody's paying attention. Okay, yeah, that's a K minus 2 there for vertex D. And right now, the thing is, vertex E has to be a different color than both D and A, which are different from each other. So that means that there are also K minus 2 choices for vertex E as well. Yeah, so that's going to also be a K minus 2. And so again, I'm going to squeeze this on the bottom here, guys. Well, maybe I shouldn't do that. Let's just go way up to the top. So by the multiplication principle, this is for case 2. Right? We have, in this case, we have, what is it? K times K minus 1 times K minus 2 times another K minus 2 and then times another K minus 2. It's actually going to be cubed, right? Cubed, and this is ways to color the graph. Okay, so this took a little more work to get both of those cases. And after we've done that, what do we need to do for a final answer? Yep, whenever we have cases, right, we have to use the addition principle, adding how many ways there were to do it in each of the cases separately. So for the final answer, we are going to get, so by the addition principle, now we are on the last line of the write-up here. By the addition principle, P sub G of K. Is everybody with me? Does it seem okay? Yeah, Kevin, am I?
If E has K minus 2 choices and E has K minus 2 choices, doesn't it saying that they have the same color?
No, these two vertices will not be colored the same. We know that for sure, but which colors are available will be different, right? So vertex D can be anything except these two colors. Whereas vertex E can be anything except these two colors. They both have the same number of choices. What the choices are will be different for those two vertices. But here we're only keeping track of the number of choices, if that makes sense. Good? Okay, great. So yeah, so by the addition principle, I'm going to add these up, guys. We're going to get K times K minus 1 squared times K minus 2, and then plus the second case, which I wrote up at the top there, K times K minus 1 times K minus 2 cubed right there. And if I just double check it with my notes, that is exactly what I have. That is exactly what I have. Okay, everybody good with that? Yeah.
Can we just say, instead of ways to color the graph, we just say K color?
Yeah, that's just a different language for it, but yeah, maybe that would make more sense. Can I? Oh, it's 5:15. Let me write down one last thing. Can I do that? I won't even charge you extra tuition. A free extra minute. How amazing is that? Just gonna write down one last theorem here, guys, and then I'm gonna tease you with something. I've got to get you to come back on Thursday. If the graph was a tree, this is Jose's question, right? Let T be a tree of order n. Then the question is, what is the P sub T of K going to be? And you might not be surprised that you can start with any vertex and color it with any K colors you'd like. And then you start radiating out, kind of the same way when we were doing the chromatic number earlier, start radiating out along the different branches of the tree, each of which will just have to avoid whatever the previous color was. And so the remaining vertices, there will be n minus 1 vertices, right? They would all have that many choices.
We were just talking about that.
Hey, I was right on cue. Yeah, that's the formula. I will write down a proof on Thursday if you want to have a nice formal proof. But here's what I want you guys to notice. This right here is a polynomial. This is a polynomial. This is a polynomial. It turns out that this thing, even did I have the null graph up here somewhere? I guess I erased it. Every graph will have a P sub G that is a polynomial, and it's therefore called the chromatic polynomial of the graph. I'll write all that down on Thursday and we'll talk more about it, but I need to give you back your papers. And then we will go for the day. Thanks for a great class, guys. I appreciate you all being here. So I'll pass these back. Robert is not here. Alyssa. And Marcus. And Jose. Jose. Ashley. You're welcome. Mason. Kevin. Lindsay's not here. Sally's not here. Keith. Tanner. Andrew. Sam. And Linda. Hamza. Juan. So. Who's not here? That one. Kyle. Marion. She is. This one. I think that's everybody for now. All right, gang, we are out of here.
I'll be here on Thursday, but
Sorry. I will be on Zoom. Yeah, unless the battery dies, I will be on Zoom. Okay, no worries. You're a teacher.
it's the same one as the quiz.
I'm sorry?
It's the same Zoom as we done the quiz. Or not the
Ye-
quiz.
Yes, it's the Zoom classroom, not the Zoom office.
We have a holiday.
You should enjoy every holiday you can. Or catch up on whatever you need to. All right, guys. Bye for now.
Thank you, Nathan.
Bye-bye. You're welcome.
Oh, yeah, this will